So today's topic is going to be about sweeping. We're going to learn how to use the sweep tool to create pipelines. And it's a pretty simple tool. All you really need is a profile sketch and a path sketch, and you just run the sweep tool and you get that. As simple as this tool is, it's actually a very common task in engineering. You do this all the time in design. Whether you're designing a refinery, a pressurizer, a sampler, a waste treatment processing unit, it goes on and on. You always have to pipe tubes in your system. So today's topic is really more about fluid power than it is about sweeping. And when you want to send out a fluid power system to a custom fab shop, you need two things. First thing is a schematic, like what you see here, and then the second thing is a rendering of the tube lines, like what you see here. So it's good to be specific about the location of your tubes. This is why I highly encourage you to also include a rendering, like what you see here. For instance, if you're designing a fluid power system for an application like this, you can see that there are a lot of restrictions on where you can and can't pipe the tubes. So only you as the engineer really know where the restrictions are. So it'd be kind of risky to just send a schematic and let the supplier kind of figure out the pipes, because you know that this is a restriction zone here. This is an alley for this tow truck to move through. So that's why I highly encourage you to render the tubes and the pipes when you create these projects. And this is why we're going to go over this lecture. And the engineers who knew how to do that were so much better off than the others that did not know. So, and I've worked with hundreds of engineers over the years, and the ones who knew how to pipe the tubes in SolidWorks, they were able to really do a better job with their projects than the ones that could not do that. But before we talk about sweeping, we have to talk about fluid distribution and fluid power, because only once you understand those two things can you understand why we're sweeping the way we are doing it. So you gotta understand fluid distribution. Fluid distribution is the design of hardware to distribute fluid from A to B. So think about it. You need to distribute water from A to B. How do you do it? Do you use a PVC pipe? Do you weld the tubes? Do you bend it? Do you put a fitting? Okay, so you can see that there'd be a lot of mechanical engineering in just distributing a fluid from A to B. So this is a very common application for cooling, as you can see here, for sampling in the oil and gas industry. It happens all over engineering, and I've had to design a couple of these systems in my career. So the first question you gotta ask yourself is: are you going to use fittings, or are you gonna use a hose? All right. If you use a hose, you don't have to worry about, it's a lot more simple because there's no fittings. And also you get more laminar flow. You see how smooth that flow is? It's not as abrupt as these 90-degree angles. So this is good because it's easier to clean, and there's less friction, and you get better flow. So that's cool. One thing is sometimes you don't get as much pressure. These are not usually rated as high pressure as hard pipes like this. And also this is not as flexible as far as disassembly. If you have a leak here, you can disassemble these two fittings and remove that, as opposed to this where you have to remove the whole thing. And if this is a fixed hose or tube, that can be kind of difficult. So figure out whether you want to use pipes or tubes on your design based on those pros and cons that I just talked about. Here's a fitting. Okay, this is that's what a fitting is. It's these little connectors. So there's the fitting. And then there's the tube. All right, so you can see that has a little bit of a better radii. So there are many kinds of fittings out there. Back then, really, fittings were just threads or they were welded. And that was a problem because whenever you needed to remove a tube, you had to torque the entire assembly. Okay, and that was a huge nightmare. So then that's where the two-ferrule compression fitting came out. This was a revolutionary design where the ferrules bite into the tube and cause a seal. Meaning you no longer need to torque the entire assembly to disassembly. You just torque this nut, it releases the ferrule, and you can connect it and reconnect it as many times as you like. So this was revolutionary, and it caused so many companies to become billion-dollar companies just from this innovation. There are other kinds of fittings though. This one is a quick disconnect, so it's designed to release on and off really easily. They don't hold a lot of pressure, but again, it's nice that you can just connect and disconnect without any tools. Same with these ones. The push-on fitting is using a collet, and you got to press this collet to release it. Again, it doesn't hold a lot of pressure, but again, you don't really need a lot of tools. This is used a lot in pneumatic systems, so where it's like low pressure air systems, they use this a lot. And then barbed is just you got one-sided barbs that kind of bite onto the onto the tube. They're not very easy to remove, so I don't really like these, but I've used these three a lot. This is just using an O-ring for the sealing. Another way you can connect fluids is through using NPT thread. So here I talked about different techniques for fitting design. The NPT thread is another way that you can seal a connection when you have fluid running through your system. So I've talked about this in the hole dimensioning lecture, but really again, there's taper. These threads are tapered. They're at an angle so that it seals when it fastens with the internal screw threads. And then what you can do is you add Teflon tape around it so that it seals even better. So again, this is really a good solution for fluid distribution. Again, this is one of my favorites. I really like this and these three here. So those are highly recommended on your designs. So now that we understand the fitting, we gotta understand how they're configured. You can buy these in a cross shape, in a T shape, in an elbow shape. But again, like I said, notice how much complexity goes through these things. Okay, there's a lot of complexity that you're including in the system when you use fittings, as opposed to just like the tube where everything's already connected. But again, I've already talked about the pros and cons. Again, this is just showing you that yes, fittings can be purchased in different configurations. So let's talk about how a tube is bent. Let's say you decide to go with tube bending, okay? You gotta use a tube bender. You can use a CNC tube bender or a manual one, but it's really just like what you see here. You have a mandrel that goes inside to hold the shape, and it bends the tube, the diameter that you want. So it's good that you know how to manufacture the tubes that you specify. But if you're not careful, you can get these distortions. You can get wrinkling or you can get buckling and things like that. So you gotta know what you're doing. Usually engineers, they don't really spend a lot of time worrying about these defects. They mostly worry about the specifications so that your design is going to be successful. But again, the more you know about these things, the better specifications you'll be able to define. So the more the better. So another piece of hardware you might want to know about is the valve. The valve is just a switch. It's an on and off switch. You rotate it one way, fluid goes through. You rotate it the other way, fluid doesn't go through. And a lot of times when you're looking at some refinery or something like that, you're not sure if it's on or off. And because sometimes they don't label that stuff. So one rule of thumb is if you look at the handle, if it's aligned with the pipe, it means it's on. If it's 90 degree to the pipe, it means it's off. So that's kind of the rule of thumb if you're not sure. But you can always test it, by doing some troubleshooting and using gauges and things like that. There are different kinds of valves. The one I just showed you was a ball valve. This one is very popular. It's just a through hole on a ball and you just rotate it and there's a little bit of like O-rings here to seal it. But there are other kinds like gate valves, needle valves, butterfly valves, and they all have different purposes. Like, for instance, a needle valve is supposed to be very precise, like very incremental. All right. And when you become like a product engineer, you have to be like an expert in these products. Let's say you're working for a valve company, you have to be an expert as far as why is there a fillet here? Why is there a cavity here? Why is this material, rubber? Or why is this stainless steel? Why is this assembled here? Can this work without this piece? So you got to really understand every little detail of these products when you become a product engineer. So once you understood the hardware, you got to figure out how to route your pipes. I mean, are you going to just do a spaghetti job where this connects to that and that connects to this? Or are you going to have something a little bit more organized? Are you going to have some kind of system? It's kind of like designing a highway system in a way. I mean, when you want to get from A to B, think about it. You got this huge highway with like 5 lanes that are designed to be continuous. You don't have a lot of stop and go traffic in a highway. That's so there can be a lot of flow. That's so that a lot of people can get where they need to go. Kind of like the arteries in your body. You have those major arteries that flow all this blood throughout your body. And then you got a bunch of tiny branches like what you see here that are like the exits that go to the destinations that they need to go. So my recommendation is be as organized as you can and have a system. Okay, have a system that makes sense because you have to be organized. Don't be lazy on being organized because your systems are only gonna get more complicated, and you gotta really hone down on your system. So one thing you'll notice is that everything's orthogonal. I don't see any angle. Don't go crazy with those angles, okay? Don't go crazy with the curves. Everything's really nice and orthogonal. That's good. Try to stick to that. And then, like I said, also shoot for laminar flow, like what you see here. Try to have as much of a fillet as you can because laminar flow is very efficient. So again, I talk about that. We actually study the effects of turbulence and how it can cause eddy currents and how it can cause disruptions in our flow. We will study that in my FEA lecture, but for now understand that try to have a good amount of a radii on those corners. So now that we understood the hardware behind fluid distribution, let's take this to the next level and talk about fluid power. Let's talk about, well, how can we use this fluid distribution hardware to generate power? Okay, and again, this is referring to a division of machine design which focuses on the organs of a machine. Okay, on the organs, on the hardware that makes a machine run. So, up to this point, we've talked about the weldment, which was a skeleton. We talked about the sheet metal, which is the skin. Now we're talking about the organs that do the work. And there are 2 ways that this is done. It's done through pneumatics and hydraulics. Pneumatics uses compressed air as the source of energy. Hydraulics uses compressed oil as the source. And again, these are analogous to the muscles and the organs in the body. So these systems always start with a schematic. They call it the P&ID diagram, process and instrumentation diagram. And I've talked to a lot of engineers who work in chemical and processing companies. They say, oh, wow, if you know P&ID, that's a real plus. So it starts with this, and it's pretty much just a kind of like a diagram that shows you how the fluid flows throughout the system. And we're going to study how to read these. We're not going to study how to make these because that's kind of out the scope of this class, but we're going to learn how to read these because I've had a lot of times where I've went in an interview and and they've asked me to say, hey, what's going on in this schematic? Later in my career, when I was a little bit more experienced, I was creating a lot of these from scratch. But in the beginning, I was learning how to read them, and this is why I want to spend some time understanding how to read these, so that you're a little bit more seasoned when it comes to this division of engineering. So it starts with the power. Okay, this is the symbol for it, and usually it's followed by the quick disconnect, so you can easily connect it on and off. But there are many different power sources in a factory. In a house, you have like different lines going in and out of it. You have a sewage line, you have a power line, 110 volts AC, you have a water line, a gas line. In a factory, you have many other sources of power. You have shop air. A lot of times you have nitrogen. You have argon gas if you're welding. You have deionized water. Okay, you have many more lines. So in my experience, I usually start with shop air. Reason for that is because shop air is there's a lot of it. It's abundant. Okay, you don't need to bring a truck to refill it. Pretty much the way it works is the factory has this huge compressor that just takes the air from the atmosphere and feeds the plant. Whereas nitrogen needs to be imported from a truck, so that's more expensive. But sometimes you have to use nitrogen because you're working on like some super clean application that can only use nitrogen to run through. So that was one situation for me once. So just be aware, try to pick a power source that makes sense, that has the right pressure that can feed your system. So once you have the power source nailed down, you gotta include one of these. It's called an FRL, filter regulator lubricator. And it's just something you include on all your pneumatic systems. Okay, so you have your quick disconnect, your power source, then it starts going through these. Alright, so let's study this. It's got three pieces. The first piece is a lockout tagout unit. So if you remember, this is a protocol in manufacturing it's for safety. It's to prevent a dart injury, okay, which means a serious injury. And whenever maintenance is done on a machine, you want it to be locked out. You want it to be lockout, tagout, okay? You want this to happen. So there are many different gadgets to make a machine locked out before it can be maintained. In this example here, you have this switch that gets rotated. It's got some sort of spring inside, but you rotate it, and this notch matches with a notch on the lower end, and you place a lock through them to make sure that the machine does not run. So this protocol, I don't remember when it came out, but there used to be a lot of situations with this. At some point, a lot of people were dying. For example, classic example, someone, under the truck is doing maintenance, and then the guy starts driving. I've heard that story a couple of times. Okay, so it's a very, very serious protocol in the industry, and that's why I encourage you to include this unit on your FRL. The next piece is where the lubrication happens, where the regulation happens. All right, so a lot of times you want to tone down your incoming pressure, just because you can't really control the inline, but you can control the outbound a lot more by toning down the pressure. So this is what this regulator is for. And then filter, just to clean it up. So it's just something really generic that you want to include on your system. Finally, this is another safety device. It's called a dump valve, and pretty much it connects to the power system of the machine, and when the power goes out, it releases a valve that dumps the energy to atmosphere. So it's a safety mechanism, because you don't want trapped energy in your system after a power outage. You don't want to, turn the machine on and realize all these actuators are flying all over the place. You want to exhaust all that energy. So this is why you want to have a dump valve. Okay, a filter is just to clean up the air so it doesn't damage the downstream components. And pretty much it's pretty simple. You have this upper unit, you just replace it whenever it's bad. Then you have another regulator. Okay, the one I talked about here is really generic. This one's a little bit more specialized. So it's always good to have a dedicated regulator on your machine. This one is just a manual regulator. You just move the knob and the pressure changes. But later in the lecture, I'm going to talk about an electroproportional regulator, which is so much nicer than this. It's connected to the PLC and gives you direct feedback. I'll talk about that later, but the principle is the same. It just regulates down the pressure. Alright, now we're starting to get into the control system, and to do that you need to have a control manifold. Alright, let's see. So in this control manifold you have an inline and an exhaust. So if you look at the schematic, this is just representing this. I know it's kind of weird, but it's the same thing. So this is the supply here. Okay, see, this is the same thing as this. This is why I'm showing you two things. I'm showing you the symbol and the model. I want you to get used to seeing the correlation between the two. So energized air, right, shop air or whatever, goes through the supply and feeds these two control valves. See these control valves? The reason there's two, I actually just needed one for this example. The reason there's two is because when you buy these cassettes or manifolds, the smallest you can include is 2. You can stack as many as you like. I mean, it's up to like 20 or something like that. And then there's a giant tie rod that sandwiches all of them. But the reason I have 2 is because that's the minimum amount it will let me. And what you'll notice here, what I did is I plugged them. I plugged the one I don't need, and then I left these 2 open for the one I need. But anyways, this is where the supply line is, and then there's the exhaust line. You see this? This line is the exhaust. This line is the exhaust, and they're connected. See, they're connected. So here's the exhaust, and this is a silencer. The silencer is used to like absorb the oils and reduce the sound. If you've ever walked in a factory, you'll hear a lot of like popping sounds here and there. Usually in an assembly plant, you'll hear that a lot. And really, that's just from the exhaust of these manifolds. So a lot of times it's good to include a silencer. And then finally, you have this solenoid control. So this connects to the PLC using a D-sub connector cable, and it will energize the control valves. Okay, let me talk about that in just a second. But for now, understand that this is just a box with holes. That's it. There's holes for the exhaust and holes for the supply. Okay, so let's talk a little bit more about the control aspect. The control actually happens on the control valve. It doesn't happen on the manifold. The control valve has a spool inside, okay, to change the state of the energy. So the spool is going to move in 3 locations. Let's talk about that. See, these are the 3 locations. 1, 2, 3. These are 3 states, just like a comic book. In a comic book, you have 1 state, another state, and a 3rd state. Okay, so let's see if we can figure out how to read these. First of all, you gotta understand what this is saying. This is saying this is a 5-3 control valve. 5 ports, 1, 2, 3, 4, 5. 3 positions. Okay, that means I can move this handle 3 positions. 1, 2, 3. So that's what that means. Okay, so now that we get that, let's talk about those 3 positions. If I am in position 2, in the center, I'm saying that the supply, which is port 1, see this port 1 here? The supply here is going to be energized. 2 and 4 is going to exhaust the atmosphere. If I am in position 1, I move this handle. The energy from 1 is going to go to port 4. See, the energy is going to go 1 to 4. And then port 2 is going to exhaust the atmosphere. As you can see here, here's port 2. As you can see here, 2 goes to atmosphere. Finally, if I go to the 3rd position, the power goes from port 1 to 2. So the energy goes through here. And then port 4 is exhausted to atmosphere, okay? So let's talk about a few things. Let's look at this diagram. So you see how the spool is moving? When you move that spool, you redirect the energy. See, there's a similar diagram that I just showed you. You redirect the energy from one place to another, and when you do that, you can do work. You can move a piston up and down. You energize one side, you exhaust the other side of the atmosphere. You energize the other side, you exhaust the other one atmosphere. And this is how a lot of like muscle is done on like an excavator, on like an assembly, okay, on an assembly line or anything like that. It's done like this. So you may ask yourself, well, how are you moving that spool? The way I was actuating the spool in the previous example was with a mechanical handle. But in an industrial machine, you don't have the time to manually move a spool. So what you do instead is you need to use automation. And you do that using electromagnetism. And it's kind of a cool concept. Pretty much, if you connect a battery to a coil, all right, and you kind of make a spiral out of that coil, it will turn into a magnet. And if you disconnect this wire, the magnetism goes away. So it's kind of weird like that. Not everyone really understands why it does that, but it's not so important as to the why. It's more important as how can you use that? How can you use that to your benefit? So one of the reasons this is so powerful is that you can convert electrical energy to mechanical energy with this mechanism. And this is how I'm able to actuate this spool automatically. So for example, you see how it's got this symbol here? That means, this just means spring return. When you see this symbol here, it means it's actuated by a solenoid instead of a mechanical lever. So what happens is you energize the magnet, okay? You energize it from here, okay? There's the battery, there's a power supply. You energize it through this D-sub connector. It connects to this solenoid. Inside the solenoid, see there's a little, I think it's in the back, there's like a little connector here that connects to the D-sub wires, and it will energize the solenoid or de-energize it. So let's talk a little bit about the electrical system that's powering this fluid power system. It starts with a power, okay, just like fluid systems, usually 110 volts AC, and you convert it through to 24 volts DC. This is very standard for machine design. You convert it using a power supply. And I got switches here, okay? I tried to model these wires as realistically as I could so you can get an idea of how to implement this in the real world. But really, the idea is the same. This is all you really need to understand about electricity to understand any control system. As complicated as they are, this is all you need to understand. And here's the deal. You have a battery, you have a switch, and a resistor, okay? So here's the deal. When you open the switch, light turns off. When you close the switch, light turns on, okay? That's powerful because now it tells me I'm onto something. Now I can implement a control. I can implement logic. So here's how this works. You press this button, energy goes through the wire, goes through the D-sub connector that's connected here, goes through the cassette manifold, energizes the solenoid inside the control valve. Inside the control valve has one of these coils, and guess what? The spool will magnetize one way or it will magnetize the other way, okay? And that's kind of how this system is implemented. So that's kind of like the control of this. Now let's talk about the actuator. The actuator is what does actual work. And there are many different kinds of actuators. There's grippers, there's cylinders, all right, the list goes on, but the idea is the same. You're always trying to move something. And one of the things to consider when you specify a cylinder is whether you want a double acting cylinder or a single acting cylinder. So here's how this works. A double acting cylinder is more complicated. It's got two ports, meaning you have to energize one port, exhaust the atmosphere, energize the other port, exhaust the other atmosphere. So there's a little bit more complexity, but you can do the same stuff, the same motion with a single acting cylinder where you use a spring. So you energize the piston and you exhaust that same port to the atmosphere and the spring pushes it back. So a lot of times this is more convenient than this, but sometimes you need a little bit more precision on your actuation, and this may be a better option. So in one of my old designs, I had a table like this, okay, that needs to index. And inside the table are fixtures, as you can see here. It clamps on this workpiece so that work can be done on it. So I had to make a decision. What kind of cylinder am I going to include? Am I going to spec a double acting or a single acting cylinder? And the reason I decided to go with a single acting is because it's a lot more simple and I do not need to be a real precise motion for clamping. Because think about it, I mean, if I use a double acting cylinder, I mean, that'd be two ports for each of these. Then I gotta bind it to my rotary distributor, which I really don't even have that many ports to begin with. It would have been a cluster. So this is why a single acting made a lot more sense for me in this application. So I wanted to show you an industrial example of a completed fluid power system. So again, you need two things. You need a schematic like this that correlates to the actual model, like what you see here. All right, and what you'll notice is a lot of the concepts I talked about. Here's the manifold with the solenoids, control valves. Here are the exhaust with the silencers. You get some plugs because these are excessive. And then you have some, see these units? These are called, they bypass the master pressure of the central manifold, and you can bypass it with its own pressure because sometimes you need different pressures for certain parts, so you have to bypass it. So they correlate exactly, and these are so pretty much if you mix and match the pieces that I talked about, you can really create a wide array of functions, and this is what that might look like on an industrial project. So what I'm going to do now is start with the sweeping, and I'm given two files, a schematic and a rig. All right, so we're going to practice how to read this and implement it onto our model. We're going to use this schematic to pipe the tubes. We got to figure out where the tubes are going to go. So let's take a look at this schematic. And as you can see, here's the power source. It's going through these pieces, and we got to figure out what needs to be connected. So when you read these, you got to understand how this is laid out. First of all, these are the lines that you need to update, okay, and you need to create. And the line number changes anytime it goes through a component. For instance, if I put a T here, that line is going to be the same as this, 1 sub 1. If I put a T and then I do some really weird squiggly and I put another branch on that, that line is always going to be 1 sub 1 because it never crossed through another piece. As soon as it crosses a piece, number changes. All right, it crosses that piece, it changes. So that's how that works, and you got to fill out the pieces here. Also, what you'll notice is that every piece has a blue and a yellow fitting. I made this easy for you. The blue fitting means the inline, the yellow fitting means the outline, the outbound. And in the real world, it's not that easy. A lot of times you have to use a data sheet, or a lot of times the product doesn't even tell you what the inline and outbound is. So you have to do like some testing. But I try to make this easy for you. On every component, the blue is going to be inline, the yellow is going to be outline. The other thing you might want to do is to understand how these parts look like. So if you're new to this and you don't know how a filter looks like, go on the filter here and type in filter. Okay, alright, that's the filter. Let's type in valve. Okay, that's the valve. Okay, you just type the name, okay, on this filter box and see what is what. Once you've done that, look to see how they're connected. It says, alright, quick disconnect is connected to the manual valve. So that means I need a line that connects from here to here. Oops, to here. Okay, these two need to be connected, okay? So, that's the exercise. You're going to read the schematic, and you're going to figure out where the lines are going to go. So once you figure out that, now you're ready to run the sweeping. To run the sweeping, we're going to use top-down assembly using new part. We're going to initiate it here, and we're going to start with a circle. I'm just going to hover over to catch a concentric circle and start building the profile. In this case, it's going to be 0.25. How do I know? Because when I look in the schematic, it says shop line diameter 0.25. Okay. In the newer SolidWorks programs, you don't need to spec the profile sketch for a sweep, but in the older versions you still have to do that. I think it's versions 2018 and earlier, you still have to spec the circle. So once I determined the profile sketch, I need to determine the path sketch. To do that, I'm going to click here 3D sketch like we've learned, and I'm going to click the line tool. And then what I'm going to do is just draw a line. So this is my second sketch. I'm going to draw a line that goes all the way through. So here I am connecting where I left off. Alright, so per the schematic, I know that this is going to go through the valve here, and then I'm just going to eyeball where I think this is going to go, okay, and then it's going to complete on the supply line. I'm doing one continuous line because a lot of this is presentational. I just want to communicate where I want my tubes to be, alright. I don't even need a detailed drawing for this. This is talking about a very generic application, okay. Well, on some applications you do need a drawing for the tubes with actual specifications for these angles, but not for something like this. This is just to say, okay, this is where I want the tubes to be. Once I've defined the location, I'm going to clean this up a bit by adding a concentricity mate with my line. So what I'm going to do is hold shift and select the point on the line and the edge, and you see what happens? The concentricity mate shows up, and this snaps to the center. So I'm going to do that a couple more times. 1, okay, 2. And you hit concentricity. See, the line moved towards the center. So I'm going to do that all the way around until it's all cleaned up. So I went ahead and cleaned up our path sketch, and you'll notice that every line that goes through a component is black. It's black because I've added that concentricity mate. So I've selected an edge, I selected a point, and it made it concentric, as you see here. So now what I'm going to do is add a 0.5 fillet on each of these corners. Because remember, we're looking for laminar flow. And you know, when you're using tubes, that's your opportunity to really add as much of a radii as you can. So as you can see here, now it's a lot cleaner, and I now have a completed path. So now that we've completed the sketch, I'm going to exit out of that, and I'm going to select both. Here's the profile. Okay, it's a circle we created. Select the path. I'm going to go to features and hit swept boss and base, and you can see the profile that was generated here. And again, like I said, in the older versions of I'm sorry, in the newer versions of SolidWorks, if you need to sweep a pipe, you don't need a circle. You can just select circular feature and spec a diameter. I think that was in version 2018 or something like that where that came out. But if you're using something earlier, you got to select both. You click OK, and there's the result. So if I exit out of the part, there's the result. There's the tube that's gonna run our system. So I went ahead and created the second tube, as you can see here. I did it in one piece. So really there's only 2 tubes in this. If you can make these with the least amount of tubes, that's always good. So as you can see, we have the... Alright, let's just talk about what's going on here. We got power, goes through the power supply, goes through the switches, goes through the D-sub connector, inside the control valve. Then, based on what you press in these buttons, it's going to direct the fluid either to 2 or to 4. Okay, so when you move that energy to 2 or 4, it's going to move this gripper, either close or open. So in the end, you press a button, it's either going to open, you press another button, it's going to close. These are just speed controllers. I highly encourage you to include speed controllers because a lot of times if you don't, it's going to slam. The actuator is going to slam back and forth and it's going to damage your actuator. The speed controller is like a regulator. You just knob this, you just adjust this thumb screw and it will, like a needle valve, it will regulate down the pressure inside the actuator and kind of cushion the actuation. So it will make your actuator last a lot longer. So again, to build this tube, I did the same thing as what I did here. I created a 3D sketch, I created a profile sketch, and I ran the sweeping tool, the sweep tool, alright, sweep tool to generate the 3D model that you see here. So let's take a look at the homework now. Okay, the homework can be found on here, under homework number 7. And what you will get is the instructions, a schematic, and a rig. When you download the rig, you got to extract it. You right-click, you say extract all, and you'll get access to the model, which will look like this. This is a pressurizer, okay? It's very simple. This uses a PLC to control the pressure, but based on what you type, it's going to energize and control the system to deliver pressure on the outbound, as you can see with the provided schematic. So this is an interesting system because you have a pneumatic system here control a hydraulic system. Okay, what I mean by that is water is running through this, air is running through that, and this is energizing the fluid system, the water line. So that's actually a very common setup in a lot of designs on a lot of machines. So you have to pipe the missing lines. So you have to do exactly what I just did and apply it here. So these are the lines you have to include. The water line is 1/2 inch, the nitrogen line is 1/4 inch, and the yellow lines are out ports and the blue lines are in ports. Also remember the nomenclature. See, I sub 2, this is still I sub 2, this is still I sub 2 because it never passed through a component. As soon as it passes through another component, the name changes to I sub 3 and so on. So that's what you got to understand. So read that and see how you can apply it to this. Let's talk about a couple things related to the P and ID diagram concepts. You can recognize a lot of the hardware that we talked about on the tutorial, but let's talk about some of the new hardware. This is an electrical proportional regulator, which I really like. And the idea is that you can connect the PLC. You can connect the PLC to these wires using the current. Okay, usually you don't use digital signals for this because you need variation. So you have to use an analog signal from the current through the EP regulator. But anyways, what I really like about these is that you can just type in 50 psi, 75 psi, and this increments. The readout is like perfect. It's like 60 psi, 70 psi. So I really like that. As opposed to these regulators where you modify them with your hand, it jumps up and down and it's very difficult to control. So I really like these. This is just a regulator. It's the same thing as this, but it's used for higher applications. Okay, it's right here. It's used for higher pressures, I mean. Okay, so sometimes when you need to work with different pressures, different temperatures, you need to look at a completely different catalog, and your supply options are going to be so much less. Sometimes you have to search the entire world just to get a regulator for like 20,000 psi or something like that. Or you have to custom design it because there's just not a lot of companies that can deliver that specification. So anyways, this is a regulator for that are rated to 10,000 psi, so this is why we have that. Here's a pump, and it's kind of interesting. This pump can deliver 10,000 psi. It's right here. Yet you're feeding it just 45 psi of air. So the reason it can deliver 10,000 psi of water from just 45 psi of air is because of this mechanical advantage that happens inside the pump. And it's just kind of interesting how that works. So you feed it here, there's the air, and then the outbound is on this yellow fitting that is displayed there. Also, another piece I want to talk about is the check valve. The check valve just means that the fluid can only go one direction, meaning the fluid can go this way, but it cannot go backwards. So this is to prevent a backflow or something like that, to prevent damage to the upstream hardware. Also, what you'll notice here is an actuator. This is just a valve, a ball valve, like we've already talked about, but it's got this weird actuator on top. Reason for that is because it's automatic. It's not those manual valves where you can move it with your hand. This is actuated with air. So when you energize air into it, all right, it will either turn on or off. Okay, so it's just a fancy large device just to turn the valve on and off, and it can be controlled through a pneumatic system that's controlled through a manifold and through the PLC. Finally, the last piece I want to talk about is what you see here. This is called the relief valve. It's displayed here. And the reason we have that is because for safety. So, for instance, think of a scenario where the pressure's building up. Okay, we don't know why it's building up, but it's going 5,000 psi, 10,000 psi, 15,000 psi. It's just going higher and higher. Something went wrong. We don't know what, and something's gonna explode. Okay, we don't want that to happen. So what happens is you put a relief valve. The relief valve is set to a certain pressure. You just modify this knob. You just turn it. You turn the knob so that at a certain threshold, let's say at 10,000 psi, it releases the pressure to atmosphere. And in this way, you prevent trapped energy from building up and causing an explosion. So in high pressure systems, I highly encourage you to always include a relief valve. So if you're not sure how this is going to be graded, download the error cards Excel sheet from the start file. So it's right here. Just download that. And I know this is not the cleanest thing, but go to the index, all right, and look to see homework 7. Look to see what the errors are for this. As you can see, it starts at 57. So to get the hyperlinks, you gotta go to the home, and you gotta type in 57. So you can read through these, but it's pretty much just what I already talked about. Okay, so make sure that it matches the schematic, make sure the diameters are okay, make sure the concentricity is okay, make sure the tube goes inside the fitting, make sure the flow looks okay, that it's realistic, and that's really what I'm looking for with it.